Hi and welcome back to Power Electronics lectures, and today we are going to cover thermal consideration. This is one of the important topics. Sometimes they are ignored in the curriculum of Power Electronics or sometimes delayed too much, so the learners actually don't feel the importance of this topic. So that's why I maybe this time organize it to be introduced earlier before even we talk about switches, because later on when we talk about switches and participations and advantage and disadvantage, the thermal consideration will be also considered during explaining these switches. So today we will consider talking about this important topic. One of our previous videos we have discussed the linear operation and the switch operation for example for transistor, and both have been used to step down the voltage from high voltage to lower voltage, but both of them they dissipated different values of power. And for example, for the linear we have seen something very high. For the switch we have seen something very low, and when we use the anti-spice it's not zero but still some significant value. And regardless of high and low, this power dissipation will be translated to heat finally. And if I didn't consider good design for the heat, I will came up to the maximum and finally I might damage my transistor. So every MOSFET or transistor has a data sheet, and you have something called absolute maximum ratings. And let's look at the continuous drain current here. We have two values, and these two values at different temperatures. So I can use this MOSFET, for example, to pass or to flow 8 ampere if I maintain the temperature of the case at 25 degree. But if the temperature of the case raised to 100 degree, I can't do 8 ampere again. I have to reduce it, or the maximum is reduced to 5. So see, this reduction is from 8 ampere to 5 ampere. It's not small reduction, is very significant reduction. And let's link this with the power dissipation. The maximum power dissipation at a 25 degree is 125 watt. But if the temperature is increased, so this one is not anymore working. So we have to consider this MOSFET maybe to be 100 watt or even 80 watt. And if I keep pushing that transistor to pass the same voltage and current, I will end up damaging my MOSFET. So let's link this figure here with this figure, which is called linear derating factor. That linear derating factor, it says it's 1 watt per Celsius, per degree Celsius. That means for each 1 degree Celsius increase above the ambient, I will lose 1 watt of the capability of dissipating power. That means if I have 10 degree above the ambient instead of 25, I have now my MOSFET has a temperature of 35, I will lose 10 watt from my maximum power dissipation, for example 115 instead of 125. And if I'm working at different temperatures, I will lose a proportional percentage of this one. So that's why the temperature actually present for me or produce for me a new MOSFET with different ratings that I should consider, and if I didn't, I will damage my MOSFET. And the thing that I need to look at and maintain always is called the junction temperature. We have here the junction temperature. It says it's up to 150 degree. That means my junction temperature, which is the inside my transistor, if it exceeds the temperature which is in this table, that means I will damage my MOSFET. So this is my goal and objective, to keep this junction temperature to be less than 150, and to maintain also good margin, I have to keep it below 100 degrees Celsius, for example. And again, from the same datasheet IRF 840, I have seen the current now. It was 8 ampere if we consider 25 degree case temperature. But if the temperature now start increasing, and this is natural because it will increase if we draw some current, and that will be translated to power dissipation and then heat. So if, for example, I am now at 100 degree, this will come up at 5 ampere. So my transistor now is changing, and the current that was able to flow is not anymore working. And the same, for example, something called power derating curve, and some data sheets provide this curve, and one of the MOSFETs is IRFP 240. That curve tells us if you are at low temperatures here, okay, you can use this MOSFET to dissipate 150 watt. But for example, if your temperature is increasing because you didn't design your thermal dissipation well, and you didn't consider, for example, a cooling element or a fan or a heat sink, so this will increase. Maybe, for example, 100 degree, I will come up with 60 watt dissipation maximum. That means if I kept my voltage and current the same for all the period while the temperature is increasing, I will definitely lose my MOSFET because of the derating factor that's shown in this curve. So all this introduction is to emphasize the importance of thermal design and consideration that we have to take into account to make our MOSFET work in any different environment or ambient temperatures. So the primary goal of our design, thermal design, is to limit the junction temperature. And you might ask, what is the junction temperature? Look at the MOSFET, some MOSFETs, these are two MOSFETs and these are two BGTs, for example, and we have something inside them called a die, and that die is the silicon piece, okay, or different semiconductor material, and inside it there is a junction, okay, P and junction, P and P junction, or N channels, or any junction that will be controlled to pass the current. And inside this die, the junction, we have to keep that junction below the 150, as we have seen in one of the data sheets. So we have different shapes and different maybe texture for them, but all of these are embedded inside, and we can't measure the temperature of that junction. So the direct measurement of the junction is difficult because its package blocks access to that junction, and sometimes we have to measure this this temperature of that junction, but indirectly using the case or the body exposed metal, just to know what is the temperature of the inside, which is the junction. And to do that, we have to know the characteristics of the thermal components between that junction and between that case, okay? So this is the goal, and we have now to understand how the heat transfer from this junction to the ambient, okay? And after that, we do our calculation and really understand what is required to make a proper design. To start, we have a transistor here, and that's the die with a junction, and we have here the die. That die with a junction will take the power, electrical power dissipated, which is produced by multiplication of current and voltage, and then translate that or convert it to heat. That heat now will be flowing through the body of that die and going to the case, and that should be designed by the manufacturer to make a direct flow, or the easy way for the heat to go from the die to the case. If it's kept inside, it will exceed the maximum temperature very quickly and damage the junction. So that's why we have here the temperature of the junction, and that die is sitting on the case, and that case also, by the time while this developing higher and higher current, higher and higher temperature, that also the case will develop a new temperature but less than the junction. Now, if that is 100 degrees Celsius, the case will be less than 100 degrees Celsius. What controls how much less temperature it's called, there is a new component here between them. It's called the thermal resistance. And the thermal resistance works exactly like the electrical resistance, because the thermal resistance here, it blocks the temperature to go from the die or the junction to the case. And if that resistance is very, very, very small, that means the way of the temperature to go to the case is very easy, and all will be fine to go without any obstacles in the way, and the temperature of the case will be very close to the temperature of the junction. But if the resistance here between the die and the case very, very high, that means the junction temperature will be kept inside, and the difference between them will be also very high. This is exactly like the electrical component. And this resistance here is called R theta, okay, thermal resistance. And because R theta, this one is between the junction and the case, we call it R theta JC, or R theta junction to the case, okay? So now look at the junction, which is this inside here. We can't actually see it, but here we have the case, okay? And the case, some part of the case is exposed to the ambient. That means some, maybe the front side here can deliver some temperature to the ambient and radiate it. So that's why we have ambient temperature here, and we have something called the thermal resistance between the case and the ambient, and we call it R theta case to the ambient, okay? But because that case, okay, can also be attached to the heatsink, if we choosing to install heatsink here, we have another choice to make the heatsink here, and there is another component between the case and the heatsink, which is another thermal resistance. That thermal resistance is called case to the heatsink, okay? If we made a good contact between that case and the heatsink, and the surface is finished very well to make a very good thermal contact, for example, we added some grease or some thermal sheets between these two surfaces, this will increase the surface area that can really radiate the heat, and that will make this resistance very, very low, and that temperature developed in the case will also go and dissipated also by the heatsink, because the heatsink now will start acquiring this temperature and this heat, and raise its temperature above their fins here, will dissipate it to the ambient. So this is actually what we have. And maybe the last point here, we have another resistance, which is from the heatsink to the ambient, okay? So now the journey from the junction to the ambient, okay, it starts from the junction, through the junction to case thermal resistance, to case to the case heatsink thermal resistance, and then heatsink to ambient thermal resistance. This is the easy way to flow. We have another way here, okay, but that resistance is considered as very high, and we know the electrical current, if it finds two resistors, it will go through the least resistance way in more proportion than the higher resistance way, okay? And the same for the heat. The heat will come here, okay, and we'll find two ways, the way to the ambient and the way to the heatsink. And because we have done here a good thermal contact with very low resistance, it will prefer to go to the heatsink and dissipate it by the heatsink, okay? And the amount of heat will dissipate it directly by the case, it will be very tiny. And we will see this actually from the data sheet, where they specify this one is much, much higher than these two. And now, after understanding the flow of the heat from the junction to the ambient, and we mentioned many times resistance, and we know there is a resistance in the electrical also circuits. So is that really related to electrical? Can we really simulate the heat flow here, and we know the temperature of the junction or the case or heatsink by knowing the voltages, for example? Yes, we can really mimic the flow from the junction to the ambient by another topology like this one. Okay, that topology is using a current source that the value of that current source is the same as power dissipated. So the power dissipated here is translated to heat, but here we are translating it to current source. Okay, and that current source will push some current through these resistances, which are the exact resistances from the way the heat flow here. Okay, so we have here the junction, the resistance from the junction to the case, and then the resistance from the case to heatsink, and then the resistance from the heatsink to the ambient, and the final point here is the ambient temperature. And because we consider sometimes the ambient temperature to be a constant, for example 25 degree, so that's why we have set here a voltage source. That voltage source has a 25 volt, and the volt here it means that the Celsius degree. So the temperature at the ambient here will be 25 Celsius degrees Celsius. And if you look at the circuit here, I think it's very easy circuit, because you have defined current, okay, and that current will go through this resistance and will develop some voltage. Okay, that voltage, it's the difference between that junction and that temperature case. Okay, and will also flow through this resistor here and develop also another voltage, and also will flow this through this one and develop another voltage. And we know this ambient temperature, we know the current and the values of this resistance, so all the differences here between these points temperatures will be also known. So some of these resistance value will be taken from datasheet. The power dissipated will be calculated by you, as we have explained before, and the ambient will be considered as constant as 25 or other temperature values according to what is given. And that enables us to estimate the junction temperature that we can't actually measure, okay, directly. We can estimate or calculate the junction temperature by knowing all these resistances and the power dissipation, and also we can also estimate the temperatures at the case and also at the heatsink. So let's now go another step and see how we really translate that circuit to something that we can use in any simulator, and we can run some simulation exactly like calculating Ohm's law. So the thermal resistance is a component that has 2 points difference in temperature, okay, which is TJ and TC, and that TJ junction and case, the difference between them will be directly proportional to the power dissipated. And after some experiments, you will find that the relation between the difference of temperatures here and power dissipation is controlled by the thermal resistance. So now we have different temperatures here. The difference between them is controlled by the power dissipation times the thermal resistance. By taking and manipulating this relation a little bit, we will come up with this relation, which is the thermal resistance equal the temperature difference between these 2 points divided by the power dissipation. And if we compare it with the Ohm's law, electrical Ohm's law, we find the electrical Ohm's law, okay, electrical resistance equal the difference in voltage between that point and that point divided by the current, okay. But in the thermal resistance equal the difference in temperature here, okay, between that point and that point. So the temperature difference is equal to the voltage difference divided by the power dissipation. So that's why we represented the power dissipation by a current source, because it mimics the electrical current source. And now by taking this equation a little bit more, we have the power dissipation here that's considered as a current source, and that will go through the junction to case thermal resistance. Look at this one, junction to case thermal resistance. And after that we have 2 ways. The first way is from the case to the ambient, and the second way is from the case to the heatsink. So once we just came up to the temperature of the case, we have 2 ways: the case to the ambient, and it reached the ambient temperature here, and also the case to the heatsink. And after going from the case to the heatsink, we have also another one, which is from the heatsink to the ambient, okay. And because this one was very large, so that's why I ignored this in the first graph. But here I just want to consider it because I want to deliver my full view. Okay, so now we have current source and we have voltage here, constant voltage. Okay, that makes this point constant. The temperature at any point here is the same voltage we calculate for this electrical circuit, and the current here, the value of the current source here, okay, is actually the same as the power dissipated calculated electrically. And the temperature or the thermal resistance here can be taken from the datasheet or the datasheet of the MOSFET or datasheet of the heatsink itself. And you will find some datasheets calculated or presented as how many degrees per watt or how many kelvins per watt. If you find this or find this, they are the same. Why? Because the increment in Kelvin per watt, it's exactly the same as increment of degrees per watt. So it's a ratio equals a ratio. Okay, so that's why if you found Kelvin or degree, don't try to convert. Okay, it's just take it as it is because they are equal. And if you look at this model, this is the electrical model. And if you go through some references, for example, books or papers, you will find maybe a little bit different models. Okay, one of them they use this this current source, and that is floating. But maybe the correct one is to consider this current source is reference to the ambient temperature, because the definition of the power dissipation is the power dissipation that's converted to heat to raise the temperature of the junction above the ambient. Okay, so that's why maybe this one is more accurate. And some references they just attach it to the ground, which is 0 degree here. Okay, so if you consider this one or this one or this one, the good news is they are bringing to you the same answer. So don't worry about which one you find it, which one is correct or wrong. No, all of them are right and correct, and they can be considered. But maybe this one and this one can be easily drawn in electrical simulator and circuit simulators like AltiSpice, and can be used for calculation of these temperature points here. And maybe in this module I will consider this one because it's easy for us just to draw it and just to bring all these calculation very easily. One important point, which is all these models are steady-state models. If you also go through some references, you will find some references adding some capacitors across these resistors because they want to say the growth, okay, over time of that temperature. But these models are giving us the final temperature. They don't actually introduce to us or show to us the growth of the temperature over time, like the capacitor charging. Okay, so that's why we will consider this just for design. We want to know what's the final value to consider it if we want to use heatsink or a fan, or just we are fine with it. Okay, so we are not interested here in the transient. And if you're gonna throw many data sheets, and for example IRF 840, just to know where are these thermal resistance maybe included. So we have some parts of the tables they call thermal resistance ratings, and one of them is called junction to ambient. That means it's the R theta junction to ambient. Okay, from junction to the ambient, does it consider the heat sink or no? The answer is no. The junction to ambient means this resistor plus this resistor, they are all contained now together or combined together as one resistor, because they consider that you will not use the heat sink. So all this part now is not there. Okay, for the first item here, that means this resistor plus this resistor is 62 Celsius per watt. Okay, and that value is taken if you are considering your calculation without heatsink. You want to know if you didn't use the heatsink how much the junction temperature. Okay, so it's easy. You know the power dissipation, you know this value plus this value is 62, and you know the ambient, so it's easy to calculate the junction temperature, and you will finally decide whether it's more than 150 or no. But now we have also different values. This value is called case to heat sink, so I think we mean this one. Okay, case to heat sink, and it says here we have a flat surface and greased. That means it look like this. Okay, so it's a flat surface and the grease. That means we have some material that make a good and perfect contact between the two surfaces, because we have some defects, and that grease will fill these defects and make a good thermal contact. And this resistor here, if we done this, we will bring the resistance to be about 0.5 Celsius per watt, which is very, very low. Okay, so this resistance is very low. Sometimes we ignore it if we may consider the thermal greasing or sheet. Okay, maximum junction to case. Now we have junction to case. This one is considered also alone if you are considering a heat sink later on, and that one is 1 Celsius per watt. Okay, so the other two here are considering if I want to use the heat sink. Okay, but the first one, no, it just goes to the ambient directly. What about the heat sink? The heat sink thermal resistance, that one is brought from the data sheet of the heatsink itself. So we don't actually get it from the data sheet of the MOSFET. And here is another example, which is BJT transistor BD139, and we have now thermal resistance from junction to case. Junction to case, this is the resistance value, which is 10 Celsius per watt, and it gives us also the resistance between junction to ambient. Anything junction to ambient doesn't consider the heatsink. So junction to ambient, this one and that one is 100. Okay, so now you can really calculate the junction the case to the ambient as 90. Why? Because junction to the case is 10 and junction to ambient is 100, so the case to ambient should be 90, and that reveals that it's very, very high. That's why we usually ignore it. But again, you have to consider this value if you are using a heat sink, and you have to consider this value if you are not using the heat sink. And another third example, we have this MOSFET as well, and that MOSFET has 3 packages. This is the first package, which is TO263 or D square pack. This is the second package, which is TO220. This is the shape of the package. This is the name of that shape. And we have a third package, which is TO247. What's the point here? The point is the datasheet is giving us different thermal resistance for each package. And you have to consider not just the MOSFET itself. You have to consider also what package you will get from the manufacturer. Okay, so for example, let's see the first one, thermal resistance junction to case. Okay, so from the junction to the case, junction to the case, junction to the case. Okay, it's the same for all 3, because it's very obvious that the structure is the same, and the case, maybe the case is optimized to also to deliver the same resistance. Okay, between the junction and that case. So the value of that resistance is 0.83. Now look at the second one. It's resistance junction to the PCB. This is a new one, but it gives us just value for the first package, not the second and the third. Why? Because the first package is considered to be soldered on the PCB itself, and the PCB will be like a heatsink. Okay, so that's why it's like SMD component, and will be soldered on the surface of that PCB. And it says here that junction to the PCB, junction to the PCB through the case, it will be 30. Okay, and you have to maybe calculate also the thermal resistance of that PCB by some other ways to get the final temperature flow. Okay, But we will not consider this now. We will consider the junction to ambient. Look at that, junction to ambient. So if we are going to the ambient, that means we are not considering heatsink. So from junction to the case to the ambient directly without heatsink, okay? In those two, we have 62.5 for this one, and we have 50, which is lower for this one. Lower is better, okay? And that's obvious because this one is bigger. That means bigger surface, more radiation, and maybe it's optimized more for dissipating that heat. Okay, so I want just to highlight some differences between data sheets and how we read these values from these data sheets. And finally is the heatsink. And if you consider a heatsink in your design, I think you will find various shapes, ratings, and different series among the manufacturers. And to be honest, we can't actually bring them all in one slide, but maybe some of them are very popular, like the E series, okay, where you have to fit the TO220 MOSFET here and by some bolt, and also you can grease it, and then you consider it as a heatsink for your MOSFET. We have different shapes. I will not actually talk about them because everyone has its own pros and cons, and we really it's not an easy topic to cover. So we will consider one example, which is the E series, and that one, if you look at the data sheet for one of them, okay, it will tell you what is the thermal resistance to be considered in your calculation. And the thermal resistance here for the first one, it has different types and different sizes as well, okay, and they bring them here for us, okay. So the first one is different from the second, and the third series is by the size, height, okay. And the V and A, we have T, okay, we have V and A, V and A, V and A. It means the finish, the surface finish, and if it's grease or not grease or other things, okay. But forget this. We are focusing now on the thermal resistance. For the first one, it's about 11.4, okay, and the second is 9.5, 9, 7.5, 7.4, 6.2. And those thermal resistances have been calculated if the power dissipated is about 10 watt, okay. So these values are specified at the 10 watt, for example. But if I'm not considering 10 watt, will I find something that help me the specified thermal resistance for that power dissipation, which is different from 10 watt? And there is something here called natural convection. What the meaning of that? If you have gone to this heatsink datasheet, you will find something like this, and this is very common between the heatsink. You have 4 axes, 2 horizontal and 2 vertical. The left side with the bottom side axis, that one and that one, they are 2 together, and you might find these arrows here. That means these 3 curves here, okay, are read by this axis and that axis, okay, and those 3 are considered if you are considering natural cooling. What we mean by natural cooling, that means we don't use a fan or any other cooling element, okay. So it's just the heat sink with contact to the natural ambient, okay. So that's why it's called natural cooling. And if we want to read the natural cooling case, we have to consider these curves and these axes. For example, if I have 5 watt and I'm using the second heatsink. Second heatsink means the middle curve, and 5 watt dissipation means here, if you go like that and there, you will find 40 watt. It's 40 degree difference from the ambient, okay. So the temperature rise will be 40, and if you divide 40 by 5, you will come up with 8 Celsius per watt. This is the value of your resistance or thermal resistance, okay. Now if you have more or less power dissipation, you can also calculate that in a similar way. But if we have a fan, or we want to use a fan and we want to know if the thermal resistance is different, we can consider the other 3 curves here, okay. Those 3 here can be read by the right axis, this one, and the top axis, that one. The top axis is the air velocity. If you have a fan, you can set it on some velocity, and you can use some sensors to see what is the air velocity. For example, if I have 500 feet per minute, okay, that 500 will go to the same heat sink, which is the middle one, and then this one, okay, and go to the right, and I find the value of the heat of the thermal resistance is 4. It was before 8 without a fan, and now it's 4 with a fan. That means my fan reduces the thermal resistance and makes the heat sink and makes the transistor see the heat sink as easy source, easy sink for its temperature, and that will dissipate more heat. Okay, so these are very, very important to consider if you are looking for heat sinks. And finally, just a quick information about the heat sink. Sometimes you might consider more fins for the heat sink means more radiation and less thermal resistance, which is not actually accurate, because this figure now shows to us the inside fin spacing. So if I have many fins and they are very, very close to each other, the thermal resistance start to increase by decreasing the distance of these fins. Okay, that increasing, and that's due to the close proximity of adjacent fins, and there is no flow or proper flow will go between these fins. And if you start increasing the distance between these fins, you will bring the thermal resistance to an optimal value, but more increasing, you will end up with less surface, because if you rid of that one and rid of that one, and you have two good spacing or highly spaced fins, you will reduce the surface that's exposed to the air and this exchanging the heat with it. So this is the point of this figure. It's not your job to look at the spacing for the fins, but maybe it's just a correction of some concepts here. Okay, and the optimization of any heatsink is done by the manufacturer, and also they finally bring to you the curves that we have seen in the previous slide to decide what is the thermal resistance for any power dissipation or for any air velocity. And that brings me to the end of this slide. Before covering some examples next time in the next video for how we use that electrical model to calculate the junction temperature and case temperature or any other things, or use it for the design as well, and to decide whether we need heatsink or a fan or no. So see you in the coming video. Thank you.